Hello everyone, welcome to this new video. So in this today's video, we'll be solving the problem sum of XOR of all pairs. So this is a medium level problem, and this is the problem of the day on Geeks for Geeks. So the question says, given an array of n integers, find the sum of XOR of all pairs of numbers in the array ARR. In other words, select all possible pairs of I and j from 0 to n minus 1 and determine the sum of all. Alright, so it's pretty straightforward. We need not think much. So it's like form all different pairs possible and find the XOR of each pair and then add them up, sum them up, and that is the final answer. So these are some of the example test cases that are given, and the company tags haven't been mentioned here, but got to know that this question has been asked in coordination 1-2 years back. And the topic tags are arrays, bit magic, and data structures. And an important point to be noted, the expected time complexity is O of n and auxiliary space is O of 1. So we are not allowed to use, or we are not expected to use some extra space, and we are not even expected to use some algorithms like O of n square or something, because the n goes up to 10 power 5. So n square doesn't work out. So we need to find an optimal solution such that we do not use any data structure but still end up getting an answer in O of n time complexity. Alright, so you can see the code on the right side. We'll go through it briefly later. Let us first frame the approach and understand the test cases that are given. Alright, so these are the test cases. We'll see that now. So let us take the second example, 5976. Okay, I'll be writing this. So 5976. Alright, what are the possible pairs here? The possible pairs are 59, 59, 57, and 56. Great. And 9796. Okay, and then 76. So these are 6 possible pairs that are these are the 6 pairs possible. Now let us evaluate the XOR of each pair. All right, the XOR of each pair. So what is the XOR of each pair? So coming to 59, the XOR of this is 0 1 0 1 and 9, that is 1001. So what is the XOR? We all know the XOR of 1 and 0 is 1, 0 and 1 is 1, 0 and 0 is 0, 1 and 0, 1 and 1 is 0. Alright, so if the bits are same, then the XOR between them would be 0. If the bits are different, then the XOR between them would be 1. So 1 XOR 1, that is actually equal to 0, 0 XOR 0, that is equal to 0, 1 XOR 0, and like different bits, so the XOR is 1, 0 1, the XOR is 1. Alright, so what is the sum that's being contributed here? The 8 plus 4, that is equal to 12. So here the sum is 12. Alright, and now coming to this particular thing, so I'll just mention here this sum is 12. And coming to this 57, so 5 is 0 1 0 1 again. Let me write this with writing, 0 1 0 1, and 7, that is 0 1 1 1. So what's the XOR of this? 1 XOR 1, that is 0, 0 1 XOR, that is 1, 1 XOR 1, that is 0, 0 XOR 0, that is 0 again. So what is the sum here? This is just 2. So alright, so here the sum is 2. And now coming to 5,6. 5,6. In 5,6, the value of this is 0 1 0 1, and 6 is 0 1 1 0. So this is 1 XOR 0, that is 1, 0 1 0 XOR 1, that is 1, 1 XOR 1, that is 0, 0 XOR 0, that is 0. Alright, so here the sum is 0 0 1 1, that is 3. Alright, so the sum is 3. And now we can just remove this. Alright, and now coming to 97, this 1001, 0 1 1 1. Alright, so 1 XOR 1, that is 0, 0 1 XOR that is equal to 1, 0 1 XOR that is equal to 1, 1 XOR that is equal to 1. Great, so here the sum is 8 plus 4 plus 2, that is equal to 14. So here the sum is 14. And now evaluating the XOR of 96. Alright, 96. This is 1001, this is 0 1 1 0. So 1 XOR 0 1, 0 1 XOR 1, 0 1 XOR 1, 1 XOR 0 1. So all bits are 1, and this is actually equal to 15. Alright, this is equal 8421, that is equal to 15. And finally evaluating the XOR of 76. So the XOR of 76 is 0 1 1 1 and 0 1 1 0. So here 1 XOR 0, that is equal to 1, 1 XOR 1 0, 1 XOR 1 0, 0 XOR 0 0. So here the sum is 1. So here the sum is 1. So I'll just even remove this further. Right. Okay. So what are the total sums that we have found? We have found 12, 2, 14, 3, 17, and 4 plus 14 31 plus 15 46 and plus 1 47. So the final sum that we have got is 47, and that exactly matches with the answer of the second test case. You can even evaluate in the similar fashion for the first test case. That's nothing that we are doing something logical or something. It's a pretty thing, straightforward, applying the basic concepts of XOR and evaluating the sum of each pair and then adding them to the final answer. Great. So this is what we are doing, the basic naive approach. All right, if n would have been 10 power 4, we could have used O of n square method, found the each and every possible pair by using two loops and then evaluating the XOR of those things. That's it, we are done. But here the n goes up to 10 power 5, so that is the condition, that is the constraint we have, because of which we cannot use O of n square. So what could be an optimal approach to solve this question? That goes with the use of bits. That was the reason the topic tag that was mentioned is bit magic. All right, so we can do magic with bits if we could identify the tricks in it. All right, so a magic is only possible if there is some trick in it. All right, there is no something out of the box, or maybe that's not impossible that's being created there. It's a trick that actually works out that many of us do not know. Similarly, in bit magic as well, there is something like a trick that works out, because of which we can actually solve this problem to n goes up to 10 power 5 as well, instead of using O of n square method. So what is that? What is that approach? So let us understand that here. And first thing in understanding it is, we must understand this concept that we would get a result. All right, you would only get a result if there are some unset bits, and some set bits. All right, some unset bits and some set bits. What do I mean with that particular statement? So let us assume all the bits that we have are 1 1 1 1 1 1 1, okay, or all 0 0 0 0 0 0. Okay, so take any two possible pairs among this particular set. All right, take any two possible pairs. Let us assume I'm taking this and this, or this and this, or this and this. All right, so if you want me to put a different thing, so if I'm taking these two, or if I'm taking these two, or if I'm taking these two. All right, so what is the result of that XOR? So result of this XOR, 1 XOR 1, green XOR is equal to 0, pink XOR is equal to 0, yellow XOR that is equal to 0, because we are dealing with 1 itself. 1 XOR 1, 1 XOR 1 equal to 0, 0 XOR 0 is equal to 0. All right, there would be a contribution only if I am doing some XOR with different bits, like 1 XOR 0 would result in 1, 0 XOR 1 it will result in 1. All right, so if I'm actually on 1, if I'm actually working on 1, then I must look for zeros. I must look for zeros so that I could get some result. And if I'm working on 0, if I'm standing on 0, I must look for some ones so that I could get a result. All right, so if this would have been 0, like 0 XOR 0 is 0, there is nothing result, there will not be any formation of result. So if you're working on 1, look out for zeros. If you're working on 0, look out for ones. All right, in that fashion only we can get some result. All right, so this is the basic thing, understanding that we must have before going through the approach. All right, and now, because the approach it says that we have got a constant that we cannot use O of n square. Now let us evaluate with the help of bits. Let us understand this, let us solve this question with the help of bits. So I'll just list out all the numbers here. 5 9 7 6. All right, so what is the representation of 5? That is 0 1 0 1. What's the representation of 9? 1 0 0 1. What's the representation of 7? That is 0 1 1 1. What's the representation of 6? 0 1 1 0. All right, 0 1 1 0. Now great, now we have listed out all the binary representations possible. If I just need to keep one below the other, that would look great. So this is 1 0 0 1. Great. 1 0 0 1. This is 0 1 1 1. And 6 is 0 1 1 0. I'm just making sure in a single column, like the straightness is followed. So this is these are the representation, and now we are looking out for XOR of each pair. All right, XOR of each pair. So we are looking for 5 XOR 9, 5 XOR 7, 5 XOR 6, 9 XOR 7, 9 XOR 6, 7 XOR 6. So these are 6 pairs possible, and we are evaluating it. So understand that whatever the sum that you will be finally getting, it's just because of the bits. All right, it's just because of the sum of, like, the final sum, the final sum that you are getting is also represented with in a binary representation, right? So it might be like it's also represented in some binary form. So it might have 0 or 1 year, it might have 0 or 1 year, it might have 0 or 1 year, it might have 0 or 1 year. So this particular combination, this particular position is a result of these four XORs, right? These four XORs, like XORs at this particular position. So let us assume 0th index, this is first index, this is second index, this is third index. All right, so this particular, if the final sum that we are getting, is something like this. Like, let it have at the 0th index there is some 0 or 1, we don't know, we have no idea about it. But this particular combination, this particular not combination, this particular result at the 0th index in the final result is because of the XOR of all the numbers at 0th position, right? So XOR of 5 XOR 9 at 0th position, and plus 5 XOR 7 at 0th position, plus 5 XOR 6 at 0th position, plus 9 XOR 7 at 0th position, 7 XOR 6 at 0th position, and are we done with everything? 9 XOR 7, 7 XOR 6, okay, and yeah, 9 XOR 6 at 0th position. Okay, so whatever the result we are getting by 5 XOR 9 at 0th position, at whatever result we are getting by 5 XOR 7 at 0th position, plus 5 XOR 6 at 0th position, plus 9 XOR 7 at 0th position, plus 7 XOR 6 at 0th position, plus 9 XOR 6 at 0th position, we are adding them, and once we add them we get the final result and we represent it here. All right, we represent that over here. Great, this is a result of this particular thing. All right, this is the result of this particular thing. That is very clear, that is very evident, no need to be feel doubtful regarding it. That's very clear. Great, now we have understood this particular thing. So what are we going to do now? We are going to do, I'll just erase this part. So like I'm just explaining that in the grassroots level so that there will not be any sort of confusion. That is the reason it might be a lengthy video, but still you'll definitely be benefited out of this. So now we have understood that it is the result of all the 0th position results. Now we have already known that for one, now we are standing on this particular one. All right, now I'm standing on this particular one. So if I do a XOR with any another element, I must get a result. And what I must do a XOR with this one? Only zeros. All right, because if I'm working on one, I only need to look out for 0 such that I could get a result. If I'm doing 1 XOR 1, then I'll not be getting any result. If I want a result, then I must look out for zeros. So now I'm standing on this one. So I must look out for zeros in this particular 0th index. So how many zeros are there? Only 1 0. All right. So for this one, if I am looking out for anything that could actually contribute to my result, is this only possible thing. All right. I can only do a 1 XOR 0 so that I get 1, and that is contributing some result. If I do 1 XOR 1, it would be 0. If I do 1 XOR 1, that would be 0. All right. So 5 XOR 9 at 0th position is 0. All right, there is no contribution. 5 XOR 7 at 0th position is actually 0. There is no contribution. But whereas 5 XOR 6 at 0th position, it's giving 1. There is a contribution here at 0th column. 1 XOR 0 is 1. All right, so that is the main funda here. And now it's done. We have worked with 5 at 0th column. Okay, at 0th column it's done. 0th column it's done. And now what about 9? All right, now what about 9 at 0th column? So 9 also, it is a 1. So I must only look out for zeros, right? I must only look out for 0, and there is only 1 0. So 9 XOR 0 will only work out here. And similar for even 9 XOR 6 at the 9 XOR 6 will only contribute. 9 XOR 6 will only contribute at the 0th position. 9 XOR 7 will not contribute at the 0th position. All right. So what can we understand from this? So particularly at 0th position, how many set bits are there? 3. That are 1 1 1. And how many unset bits are there? Unset bits, or I'll just write it, unset bits, only 0. So this one can club with this 0 for a result. This one can club with this 0. This one can club with this 0. All right. So how many pairs possible? Here 3 count is 3. 3 set bits and 1 set bits. So this is 3 into 1 is equal to 3. All right. So there are 3 pairs possible that could give me a result. All right. That could give me a result. There are 3 pairs possible that could give me a result at 0th index. Now let us evaluate for first index. All right. Now let us evaluate for first index. First index. How many set bits are there at first index? So we have 1 1. All right. 1 1. How many unset are there? We have 0 0. So here there are 2, here there are 2. So finally 2 into 2 is equal to 4. So there are 4 pairs that could give me a result. So let us even see that. So for 5, what could give me a result? 5s or 9 will not give me a result because both of them are 0. All right. 5s or 7 would give me a result because 0 and 1. So 5 7 would give me a result, and 5 6 will also give me a result because 0 and 1, right? So 5 6 would also give me a result. So 2 pairs done. Now coming to 9. All right. Now coming to 9. Coming to 9, what are all the pairs that are possible? 9 and 7. All right. For 9 and 7 could be there because 7 and 9 opposite bit 0 and 1. All right. At first column. Okay, now we are done. Same is the case. 9s or 6 will also give me a result. All right. 9s or 6 will also give me a result. The reason being both of them are different bits, 0 and 1. Now we are also done with 9. Now coming to 7. So are there any bits left? Yes, 6. But it is 1, so it will not contribute to any result. All right. So that is also done. And 6, there is nothing other thing to deal. So that is the reason there are 4 pairs. 1 2 3 4. That is the reason we have got 4. All right. In the first index we have got 4. And now second index. So okay, we are done with first and second. 0 and first. Now let us evaluate on second and third index. All right. Second index. So second index, how many set bits are there? I'll represent set with S. So how many set bits are there at second index? There are 3 sets, 1 1 1, and unset only 0. So like only 1. So 3 pairs into 1, 3 into 1, that is 3. All right. So there are 3 pairs that will contribute a result. We'll evaluate what is the result that it will contribute later. Now just let us understand at that particular column how many pairs are resulting how many pairs are giving a result. And now at the third column, the set bits are only 1 and the unset bits are 0 0 0. So again here the contribution is 3 pairs. 3 into 1, that is 3. So here 3 pairs will be forming, here 3, here 4. So totally okay. Now we are done at each and every column. 0 column is done, first column is done, second column is done, third column is done. We are done. Now our task is to evaluate what is the result that we are getting from that particular column. Okay. Now what is the result that we are going to get at particular column? Now at 0th column, we have 3 pairs, right? We have 3 pairs. What is the result? That is basically nothing but 2 power 0. All right. That is 2 power 0 into these 3. 3 into 2 power 0, that is actually equal to 3. All right, because here the contribution from each result, now when I say I'm getting a result from the 0th column, that means at 0th column there is a bit, there is a bit. All right, set bit. And when we have a 0th set bit at 0th column, that is 2 power 0, that is equal to 1. All right, so that is the contribution. So each pair that is giving a result at 0th column will give a result of 1. All right, so there are 3 pairs, so 3 into 1, that is 3. Now we are done with 0th column. Now come to first column. So I say at first column I have a set bit. So what do I mean by that? I mean that there is a power, the result that I'm going to get over there is 2 power 1. 2 power 1, that is equal to 2. So 2 is the thing, right? So how many pairs are there at first? So 4. So 4 into 2, that is equal to 8. All right, 4 into 2 equal to 8. So let me highlight this with blue. Okay, 4 into 2 equal to 8. So here we are going to get 8. All right. So 4 pairs are there which are going to give me a result. And what is the result from each pair that I am going to get? 2. So 4 into 2, 8. Now come to the second column. Second column is 2 square. So second, if I mean, that means I have a set bit at second column. So what do you mean by that? 2 power 2, that is equal to 4. So how many pairs are there? 3 pairs, and from each pair I'm going to get 4. So what's the result that I'm going to get from the second column? That is 3 into 2, that is 3 into 4. All right, 3 into 4, that is equal to 12. 3 into 4, that is equal to 12. Let me highlight this again. And now coming to the third column, that is 2 cube. So when I say at third column, I mean a set bit at the third column, and if it's a set bit, that is 2 power 3, that is equal to 8. All right, so how many pairs are possible? 3. So 3 into 8, that is equal to 24. All right, so 3 into 8 equal to 24. So what is the sum that we have got? 24. At 0th bit we have 3. At first bit we have 8. At second bit we have 12 if I'm not wrong, and at third bit we have 24. So if you just evaluate, that answer would be 47. All right, 24 plus 12 36 plus 8 44 plus 3 30 47. All right, 47 is the final answer. That is the answer here. So what we are doing is we are going through each and every bit, each and every column. All right, each and every column, or zeroth bit, first bit, second bit, third bit, until 31 bits, until 31 bits. All right, 31 bits, we can go up to 31 bits, and we are evaluating the result at each and every bit. Because O of n square is not possible, we need to work on bits, we need to work on bits. That is the reason I've explained each and everything in grassroots detail. What do I mean by bits contribution? So each and every bit we are going into, and we are analyzing the result at each and every particular bit, at 0th bit, at first bit, at second bit, at third bit, and we are summing them up, finally. So what is the contribution? Contribution will only be there if there are different bits. All right, if there are different bits, and at each column there will be a different contribution from each pair. So at 0th column, if I'm finding some result from a pair, that means I need to multiply that with 2 power 0. And if in first column, if I'm getting some result, at that I need to multiply by 2 power 1, because that is the column, that is the 2 power 1 column. And at second place, 2 power 2, third bit 2 power 3. 2 power 3 is the bit, right? 2 power 3 is the value. 100 means this is equal to 2 power 3, that is equal to 8. All right, so this is the thing that we are working on, and this is actually contributing 8. That is the reason we multiply by 8 if we are on the third column. So whatever the results that we are getting on third column, we multiply that with 8. So this is the very easy, very beautiful explanation I feel I've given. So I've explained everything in grassroots detail, what are the bits and how are we using it to find this particular answer. So now let us go through the code. So firstly, in long lump sum equal to 0, and for int bit, so starting from 0th bit till 31, okay, 31, 30, 29, so on till 0th bit. And set bits equal to 0, unset bit equal to 0. So for int j equal to 0, j less than n. So like if this is an array elements that are given, so we'll be traversing on each of this element for 31 times. All right, for 31 times. So that's basically 32 times, 32n. So this is actually n. All right, so O of 32n. So this is basically O of n itself. So I'm checking at area of j and one right shift, one left shift b. All right, so when I'm doing left shift bit, so I'm checking first, initially I'm checking for this 0th position, and I'm checking for first position, and then second position I'm checking, like each and every checking position I'm checking if the particular bit is set or not for that particular element. All right, this is the way that we could check array of j and operation one left shift bit. So if I'm getting some value from there which is not equal to 0, that means array of j as a set bit at that particular bit position, at bit position. All right, so at that particular bit position we have a bit. If the end operation is not resulting in 0, it's resulting some value, that means I can say that at that particular position array j is having a bit. If it is not resulting some value that's not equal to 0, if it's returning if it's returning 0, that means we can understand that there is no set bit at that particular position. So unset bit would be plus in that case. So possible combinations are set bit into unset bit. That thing we have multiplied 3 into 1, 1 into 3, 2 into 2. So number of set bits into number of unset bits, and finally we are multiplying that with the power. So this is basically nothing but power of 2 comma I. All right, power of 2 comma I, or 2 comma bit in this case. So this in terms of bits we are doing in this fashion, one left shift of bit. So if initially bit equal to 0, that is 2 power 0 would be 1. If bit is at 1, that means 2 power 1 is equal to 2, and if it's bit at 2, 2 power 2 is equal to 4. That's what we are doing, one left shift of bit. All right, and we are adding them to the sum, and finally we are returning the sum. All right, so this is a very easy, not easy question, it's a good question, but I have made sure like you people, and I think I have put all these things in a very clear crystal fashion. So if not understood, please watch this video once again so that you'll get some better clarity. And this is on working on bits, right? It's very easy. If you could just write this on a pen and paper, using a pen and paper, you will definitely understand what are we actually trying to do here. All right, so, and we'll even submit the code for your reference and check. And okay, so this is everything's passed. So I hope you people understood this question, like mainly my solution to this. And if there are any doubts, feel free to comment that out in the comment section. And also for your reference, the codes in C++, Java and Python have been attested in the description. You can just check them out. And thank you for watching. Stay tuned.